Hello everyone, and welcome to AWCI's webinar, Sound Rated Construction, A Guide to Sound Transmission. My name is Tawen, AWCI's Education Program Manager. At this time, I'd like to introduce our presenter, Andrew Schmidt, Principal Researcher in Acoustics at USG Corporate Innovation Center. Andrew is an acoustical consultant and researcher experienced in a wide array of commercial and residential construction types. With an engineering degree from the Acoustics and Music program at the University of Hartford, Andrew's expertise spans all areas of architectural acoustics, including sound isolation, room acoustic, and mechanical systems of noise and vibration control. He joined USG Corporation in 2017 as a senior researcher in the Building Science Lab with a focus on new product development, technical support, and the creation of next-generation acoustic tools and resources. So welcome, Andrew.
Thank you, Tao. Thanks for having me today. Good morning, good afternoon, everybody. Again, my name is Andrew Schmidt. I'm happy to be here today and talking to you about a topic that is near and dear, and that is sound-rated construction. Part of what I do here at USG is provide technical subject matter expert support to our customers, and we get a lot of questions around sound, STC, and so today's presentation really gets into some of the common questions that I get, and so I'm going to try to make this valuable for both the contractor installer side and also folks that might be involved more on the design and specification side. So without further ado, here's what we're talking about. I got it broken down to 4 major topics. We're going to go through the sound transmission basics. What is STC? What is AWCI? How are these? How are assemblies tested in the lab and in the field? I'll speak briefly about field testing and what that looks like. I'm going to show you some codes and standards, some design standards and code references where STC and AWCI are mentioned and required. And then the real meat and potatoes of this presentation will be number 3 there, influencing factors. What are the details? What are the components, the configurations that really affect STC? I'm going to focus a lot on STC, but we'll touch on AWCI as well. And then I'll talk about some strategies for success, some do's and don'ts, if you will. How do we make sure that we're getting the most out of these assemblies? So let's start with the basics. All right, what is sound transmission? What are we talking about here? So really what we're talking about is what it sounds like, sound transmission, the transmission of sound to adjacent spaces, both vertically adjacent, horizontally adjacent spaces. And we're talking about not only airborne sound, but also impact sound or structure-borne sound. The laboratory metrics that we use most commonly for sound transmission are STC or sound transmission class and AWCI or impact insulation class. STC is a measure of airborne sound transmission. AWCI is a measure of impact sound transmission. So imagine footfall through a floor ceiling assembly. There are field test metrics that kind of align with both airborne and impact, and those are NNIC, normalized noise isolation class, that is a field measurement of airborne sound transmission, and then NISR, normalized impact sound rating, that is the field metric that's comparable to AWCI. There are other field metrics. I'm going to touch on just these 2 really, because these are the 2 metrics that are referenced in the IBC, in the International Building Code. So let's talk about how we test these things in the lab. This is a very simplified representation, but a fair representation of the airborne sound transmission test. This is how we arrive at the STC rating of a wall. So the ASTM standard is ASTM E90. The standard name is a bit of a mouthful, standard test method for laboratory measurement of airborne sound transmission loss of building partitions and elements. So it involves 2 rooms, a source room and a receive room. These are reverberation chambers. So they are rooms that are dominated by hard reflective surfaces. In the source room, we have a large speaker, a sound source that generates sound across all frequencies in excess of 100 decibels. In both the source room and receive room, we have microphones that measure the average sound pressure level in those spaces. So when you turn that sound source on and you measure the sound level in the sound source room, and in the sound receive room, you're going to have a difference, right? And the difference between the source room sound pressure level and the receive room sound pressure level gives you what we call the sound transmission loss of the wall in question. And that wall is built between these two rooms. Fairly straightforward test. In the field, it's ASTM E336. It's a similar test. Again, you're going to have a loudspeaker in one room. You're treating as the source room. You're going to be taking sound pressure level measurements in that room and whatever the receive room is for the wall that you're trying to test. So what does this look like? Here's a picture of our lab here at USG. We do have an accredited laboratory here where we can do this testing, ASTM E90 testing. This particular wall opening, we actually have two STC openings, wall openings. This one here is 16 feet wide by 9 feet tall. In this particular instance, in this image, the wall under test is that center part. It is 8 feet wide by 9 feet tall, and then we're using filler panels flanking that. That is allowed by the standard. The standard is quite flexible in terms of how it allows for you to test these walls. I believe the minimum sample size for a wall test is 8 feet by 8 feet. So you need to be at least that large in order to qualify an official test. So that's how we test walls for airborne sound transmission, or STC. The same exact test standard and method is used to test floor ceiling assemblies for STC. And that's kind of what's depicted here. In the case of testing a floor ceiling or a horizontal assembly, your source room is above the receive room. That red partition through the middle, that is your floor ceiling assembly under test. But the method is exactly the same for walls. You have a sound source, a large loudspeaker in the source room. You excite that room with sound levels, again, in excess of 100 decibels across the entire frequency range. You're measuring the sound pressure level in the source room and in the receive room. You subtract one from the other. That gives you the sound transmission loss of the partition of the floor ceiling assembly. There is a calculation method, which I don't get into in this presentation because I need to save time for other stuff in this presentation, other information. But again, when we do this testing, we measure across a wide range of frequencies. But then there's a calculation method, again, standardized in ASTM. It's ASTM E413. It's standardized calculation or classification for the single number metric of STC. I'm not going to go into detail on that, but it is important to reference. And here's what the receive room in a floor ceiling chamber looks like. This is taken at Intertech in York, Pennsylvania. So we are looking up at the bottom of a floor ceiling assembly that was installed for test. Above that is the source room where you would have the loudspeaker. And when we are at the lab and we build those horizontal assemblies for tests in the vertical configuration, it's very common to also run the impact sound transmission test. This is ASTM E492, the standard test method for laboratory measurement of impact sound transmission through floor ceiling assemblies using the tapping machine. You can see the tapping machine is a standardized calibrated machine that sits on the floor ceiling assembly. The standard requires that it be put in a couple different locations, couple different positions relative to the framing members of the floor ceiling assembly. You have a microphone, again, in the receive room that is recording the sound level of the impact sound energy transmitted through the assembly from that tapping machine. Similar to STC, the result here is IIC. And again, because the tapping machine is kind of exciting energy across the frequency range, the raw data that comes out of this test is what we call NISPL, normalized impact sound pressure level. It's across a wide frequency range, and then there's a calculation method according to ASTM E989 for calculating the single number IIC rating. Also, typically when doing these tests, it's not uncommon to install multiple floor coverings, finished floor coverings. We'll talk about this later, but for IIC, the finished floor itself, whether it's ceramic tile or cushioned vinyl or carpet and pad or sheet vinyl, that finished floor material is very influential on the result. And so it's quite common to test an assembly with multiple different finished floors. Here's an image of that calibrated, standardized tapping machine. Doesn't look like much here, but what's on the inside are several, I believe, half-kilogram weights on a camshaft, and they're dropped in rapid succession. So it creates a kind of this rapid tapping sound. So some important considerations when it comes to STC and IIC. The first, as I mentioned, these are single number ratings. When we do the testing in the lab or in the field, again, the field tests for both airborne and impact are very similar. You're just doing it under field conditions, slightly different ASTM standards. I'll reference them later when we look at the IBC. But you're capturing data, you're capturing sound levels across a range of frequencies, and then we simplify it to a single number rating. And it's a complex kind of curve fit calculation to arrive at these single number ratings. So they don't always tell the whole story. If you look at the raw data across the entire frequency range, you can see differences. Even if you have the same STC or IIC rating between two assemblies, you can see differences in their curves in the narrowband performance. Also, it's important to note that the STC rating, it roughly encompasses the human speech frequency range. So again, STC is that sound transmission class, the measure of airborne sound transmission, and it gives you a snapshot of how that assembly will perform relative to human speech being the sound source. Another important consideration, STC and IIC are ideal laboratory ratings. When we build these assemblies in the lab, they do not have any penetrations, there are no outlet boxes, no light switches. They are, for all intents and purposes, perfect. So that laboratory number that you see published in whatever guide or whatever literature, it represents an ideal assembly. Obviously, in the field, conditions are anything but ideal, usually. So field performance, you should always expect it to be lower than the laboratory performance. But if you follow best practices for sound-rated construction, which we'll touch on toward the end of this presentation, your field performance should be no more than 3 to 5 points lower than the laboratory ratings. I say should because, again, field conditions can vary quite a bit. So we're not going to go into that level of detail today, but we will touch on some best practices for sound-rated construction. And finally, and this is very important, I'm going to touch on this a few times today, there is variation in these laboratory tests. Just for ASTM E90, which is the airborne sound transmission test, the accepted laboratory variance, the reproducibility between laboratories, means that if you test the same exact wall, for example, in two different labs, the STC rating could differ by as much as 4 points. This is very well known within ASTM and by acoustical engineers and consultants, but it's less widely known by the design and the building construction industry. So I want to hang on that point just a little bit more here. So I'll show you an example of this variability. On the screen here is a very simple non-load bearing, what we call a 1 hour fire rated wall. So a single layer of 5/8 type X, both sides of EQ25 steel studs, 24-inch on center, fiberglass cavity insulation. So last year, actually maybe 2 years ago, there was a recent ASTM round robin. So all of the accredited labs in North America to do the STC ASTM E90 test participated in this round robin. We all tested the same walls using the same products, same configurations. The products were even from the same manufacturing runs to limit variability. So these walls were constructed at all these different labs, and everybody submitted their results. So I captured, there were 16 participating labs. One of the labs, the data was no good. So, but I captured 4 of the labs here and the results for this wall. And this roughly spans, you know, in terms of the quote unquote good data that came out of this study, out of this round robin, this encompasses the range. We saw values, results from STC 47 up to STC 51 for the exact same wall, tested at different labs. So I really, when I talk to contractors and designers, I really encourage everyone to think about STC in terms of ranges, and to really think about this variability when you're doing your design work. If you're a contractor, you inherit a partition schedule and you're trying to make sense of those ratings. Plus or minus 1 STC point, plus or minus 2 STC points is not considered really a significant difference if it's within that laboratory variability. So it's a good thing to keep in mind. The same holds true for IIC. There's another round robin happening for IIC in ASTM right now. I would expect there to be even more variability in the IIC rating, but it's good to keep this variability in mind and think about these values in terms of ranges. So let's look at some codes and design standards that reference STC and or IIC or even some of the field metrics. Again, I think Tao is going to distribute a PDF of this presentation. I have a lot of links here. All of these links are active, they're clickable, so you'll be able to click on anything that you see here that's highlighted with an underline underneath it. But starting from the top, IBC and IRC, those are, you know, governing codes, right? And a lot of, obviously in the US, we don't have one single building code, but most of our local, municipal, and regional codes are usually based somewhat in the IBC. So I'm going to show you some requirements from there. Green building sustainability, you have LEED. Healthy buildings, the well building standard references sound transmission requirements. For healthcare, you have the FGI guidelines, which has quite a bit of information around sound transmission. I'll show you in just a few minutes. For education facilities, schools, there's an ANSI ASA standard. And then for government and federal buildings, there's the GSA PBS P100. I'm just going to show you some snapshots of a few of these. First is the IBC. And in the 2024 IBC, you want to look at section 1206. 1206.2 addresses airborne sound transmission. 1206.3 addresses impact. But the minimum requirements are STC 50 and IIC 50 between dwelling units and between dwelling units and public or service areas. And this is both for horizontal and vertical adjacencies. And remember, again, these STC and IIC ratings are tested in accordance with the laboratory ASTM standards, E90 for STC and E492 for IIC. I mentioned some of the field metrics before. This is where they're referenced in the IBC in the same section. The IBC allows for field tested values to be up to 5 points lower than the laboratory tested values. So I mentioned before that if you follow best practices for sound rated construction, your field performance should be no more than 5 points lower than your laboratory values. This is more or less addressed in the code with these minimum values of 45 and 45 for NNIC, tested per ASTM E336, that's airborne sound transmission, so it's akin to STC, and NISR, normalized impact sound rating, tested per ASTM E1007, which is comparable to IIC. Here's an excerpt from LEED. And so the next two examples I'm going to show you, one from LEED and one from FGI, they're very similar in terms of showing you these adjacency combinations. A lot of these standards where they reference STC or minimum STC requirements are based on adjacencies. This type of room next to this type of room, you need to have a minimum STC of this. So that's what you're seeing here. This table is an excerpt from LEED v4. I will mention there are changes coming to LEED v5. That's a whole story, a different story altogether. I believe this table is going away in LEED v5. Doesn't mean this isn't valid and valuable. Obviously, a lot of architects have not yet adopted LEED v5, so LEED v4 and v4.1 are still active. But similarly, here we have the FGI requirements, and this is what I want to spend a little bit more time on. You'll notice it's similar to LEED, where it talks about adjacency combinations, patient rooms next to patient rooms, or patient rooms next to public spaces. What I want to draw your attention to is up in the top of the table, there's this superscript 2, and at the bottom here, I copied the footnote for that note number 2. And what you'll see here in the underlined section, when selecting assemblies based on their tested or published STC ratings, it should be noted that laboratory STC reports can, in general, be considered accurate to plus or minus 2 STC points. Consequently, an assembly with a tested or published STC rating as low as 2 points below the stated minimum may be considered acceptable. So FGI is acknowledging that there's variability in these tests, that you can test the same wall in multiple labs and get a range of results. As far as I know, this is the only design standard that acknowledges that variability. So the folks who did FGI and built this table and wrote that note, they did their homework, they know their stuff. I hope to see this in more design standards in the future. All right, let's talk about influencing factors. This is really the important stuff. And I have a big table here, and I'm going to go in order of significance, right? I want to talk first about the factors that most significantly affect STC. So we're starting solely with STC. This is airborne sound transmission. I'm really, in these coming slides, I'm focused mostly on wall types. After this section, I'm going to talk about the influencing factors on IIC. But really just starting with airborne sound transmission right now. And I really want to highlight some of the pitfalls that I see on a day-to-day, week-to-week basis with some of our customers and the questions that we get. So the first, we're going to start left to right here. The physical properties here that I want to talk about first is stiffness, which I've kind of added with resilience and decoupling. And really what this has to do with is your framing conditions. Framing conditions are 9 times out of 10, the most significant influencer on STC for your assembly. So thinking about those effective components, the framing type, whether you're talking about wood or steel, that's going to be a factor. Stud gauge, stud spacing, that's very, very important. Stud orientation, do you have a single stud wall? Do you have a double stud wall, a staggered stud wall? Are you using decoupling elements like resilient channels or sound clips? So in the coming slides, I'm going to show you examples of most, if not all, of these different factors. But what I will say, as noted on the right, generally speaking, assemblies with stiff framing conditions will yield lower STC than more flexible or resilient framing. And that's especially true in single stud walls that don't have resilient channels or sound clips or something else to add some resilience to that wall. For fire-rated floor ceiling assemblies, many fire resistant rated floor ceiling assemblies already require resilient channels to achieve the fire rating, and resilient channels are great for STC. I'll talk about that more later. The next factor or property we want to talk about is damping. What is damping? Damping is reducing energy, right? Sound is vibration, and the amplitude of that vibration, if you have a high amplitude sound, that is loud sound. So when we think about that STC test and we're blasting sound in excess of 100 decibels, that's high amplitude sound. We want to bring that amplitude down by means of that wall construction. And that is what damping is. Damping is reducing the amplitude. It's removing energy from that incoming sound energy. So what are some things that add damping to a system? Well, presence of insulation, fibrous insulation in the cavity. The insulation type, the thickness of the insulation is a factor. Multiple panel layers. So when you have, for example, 2 gypsum panel layers, one on top of the other, there are some frictional losses between those panel layers. That's effectively damping the energy as it transmits through the wall. There's also compounds. There are damping compounds that can be applied between panel layers. I'm not going to go into great detail on that. It's called constrained layer damping, but these are all different ways to remove energy or reduce energy as it transmits through an assembly. On the right in the notes, we say, okay, yeah, unfaced fibrous cavity insulation damps cavity resonance. That increases STC. I'm going to show you an example of that. And keep in mind that fire resistance designs, especially horizontal assemblies, may have very strict limitations or restrictions or caveats related to insulation type, thickness, and location in the cavity. So it's really important to follow and defer to the published designs, UL designs, GA designs, whatever they may be, especially for horizontal assemblies as it relates to insulation. And last is mass or weight. And this is, the effective components are adding panel layers, right? You're increasing the weight of the wall. Gypsum panel weight can play into account a little bit, but you're talking about small variations or changes to STC here compared to the physical properties described above, the stiffness, the damping. And so I'm going to show examples of these now. All right, so we're going to start with framing type. And so in these coming slides, I'm going to show 2 different walls and we're going to compare them. And I'm going to highlight on the right in yellow the component that we're comparing. So in this case, the wall on the top uses EQ20 19 mil steel studs at 16 inches on center. And the bottom wall, it's all the same components with the exception of the studs. We're looking at 2x4 studs, 16 inches on center. I'm also showing UL designs here. These are representative UL designs of what you're seeing on the screen. There are probably more UL designs that would apply to some of the partitions I'm going to show, some of the walls I'm going to show. But again, I wanted to include some clickable links so you can easily access some different UL designs here that might be appropriate for these different wall types. And what I will say is, in my role as the building science team lead at USG, I work very closely with our fire experts because fire and sound go together, right? A lot of times you have a sound requirement and a fire rating requirement for walls. So what we do for sound can't negate the fire rating and vice versa. We want them both to play together. So I'm going to show the UL designs in these upcoming slides, and really important to defer to those designs when it comes to the details, fasteners, fastener spacing, what is and isn't allowed in these various designs from a fire resistance standpoint. So again, back to what we see on the screen, what we're comparing here are the framing members. And so what's the difference in STC? 10 points. STC 45 with that steel stud, EQ20. Okay, so these are non-load bearing equivalent gauge 20 studs. STC 45, that's a pretty resilient framing condition compared to what you see below. The 2x4 wood studs make for a very stiff framing condition. And in this case, that stiffness has a pretty extreme effect on the STC rating, a 10-point reduction if you compare these two. So generally, steel stud walls are going to yield higher STC than their wood stud counterparts. That's going to change, and I'm going to blow that up in the next couple of slides, because once you start getting into very stiff steel studs, like 16 gauge, 16 inches on center, they start to behave a lot more like that 2x4 wall that you see on the bottom. So we'll see that coming up. All right, let's talk about stud gauge. So now we're just looking at steel studs. So the wall on top is the same wall that we were looking at before, STC 45. This is our EQ20 19 mil studs, 16 inches on center, non-load bearing 1 hour fire rated wall, STC 45. In the wall below, We're looking at the same construction, but we've swapped out those studs for a 20 gauge 33 mil stud. So this is a structural 20 gauge stud. And you'll notice I list a few different UL designs here, right? Because technically this wall on the bottom, it meets the requirements for the non-load bearing wall, U419 or U465, but it also can meet the requirements for the load bearing. The reason I call attention to this is because you may think that you don't need a load bearing wall, right? Oh, this wall is not bearing load, so I'm going to consider it non-load bearing. Okay, that's great. But your limiting heights might require that you have to use heavier, thicker studs, structural steel studs. And this is a common issue that I see all the time, where a partition schedule will list an STC rating for a wall type based on 25 gauge studs, 24 inches on center. But then that wall type, depending on where it is in the project, it could be 30 feet tall, and it needs to be built with 16 gauge studs, 16 inches or 12 inches on center. And that dramatically changes the STC. So that's really what I'm getting at here. So STC 45 for the 19 mil studs, 16 inches on center, STC 40 when you increase that steel thickness to a 20 gauge 33 mil structural stud. Okay, a 5-point reduction is not insignificant. That is a very noticeable reduction. Let's take this one step further. So again, the wall on top is the wall that we've been looking at all along, 19 mil EQ20 steel studs, 16 inches on center. Now on the bottom, now we've changed out those studs to 16 gauge 54 mil structural studs. And you've dropped another 5 points from the 20 gauge structural. You're down to STC 35. So this is the wall, you know, I mentioned that when you get into these heavy steel studs, these structural steel studs, they start to perform a little bit more like those stiff 2x4 wood studs. This is that example. So in single steel stud walls that don't have resilient channels or sound clips, your stud gauge is likely the most influential factor on STC. And I see this all the time. Again, the example I gave with limiting heights, where the STC, the design STC, is based on 25 gauge studs, but in practice, in reality, you have to build with 16 gauge studs, and there's a huge difference in STC. Doesn't matter what wall board you use, doesn't matter if you change out your insulation, you're not going to be able to overcome the stiffness of that framing. There are ways, though, and we'll talk about that coming up. So let's talk about stud spacing. Stud spacing is an influencer. It's a little less influential than the stud gauge that we were just looking at. Again, the wall on the top that we're looking at here is the same wall we've been looking at. It's the 19 mil EQ20 steel stud, 16 inches on center. The wall below uses the same framing members, but they're spaced 24 inches on center. Everything else is the same except for the 24 inch on center spacing, and we increase STC slightly. 3 points is a fair increase. Now, if we were to look at this example with multiple, if we had a 2-hour wall with 4 layers of gypsum total, the difference might be a little, it might be not quite 3 points, but generally speaking, if your studs are spaced further apart, you're going to see slightly higher STC than you would with closer stud spacing. Stud configuration, this is a big one. It's a big one, and it should be big because it's a big change in the wall system, right? If we're looking at that wall on top, this is the same wall we've been looking at in the past few examples, 19 mil steel studs, 16 inches on center. And then the wall on the bottom is a chase wall. So I know UL design U493, there are other similar chase wall designs in the UL directory. And obviously here we've added a 1-inch air gap, a whole additional row of studs and insulation, same number of gypsum panels, still a 1-hour wall, but you're all the way up to STC 60. Why? That's because the 2 separate frames, you have 2 independent steel stud frames here, and so there's an extreme amount of decoupling. You've fully decoupled one side of the wall from the other, and that's really going to improve STC. So a couple notes here. In this example, the chase wall that we're looking at on the bottom, STC 60, was with 19 mil EQ20 steel studs. You could build that wall with 20 gauge structural or even 16 gauge, and you're largely going to maintain that high STC. You might see small reductions, but as long as there's no rigid bracing between those opposing steel frames, you're going to have a high STC wall because you've fully decoupled those frames from one another. That is really the governing factor here. These chase walls we see a lot, excuse me, as demising partitions in multifamily housing. You could also build that with double wood studs, right? And you're going to get high STC, even though those wood studs are very stiff and make for a stiff framing condition. When you have that double stud separated by that air gap with no rigid bracing between the two frames, high STC will be maintained. All right, resilient channels. I'm going to spend a little bit of time on resilient channels for good reason. But again, the wall on top that we're looking at here is the same one we've been looking at in the past few slides. It's our EQ20 19 mil stud, 16 inches on center. The wall below, same framing condition, but we've inserted resilient channels, and I'm calling them high performance resilient channels. I'll speak to that in a few minutes. Resilient channels are inserted on one side of the wall between the studs and the gypsum panel. And so what happens here is we see that STC rating increase by 5 points. I'm going to take this one step further. So I want to look at this, a similar comparison with and without resilient channels, but you'll notice I've underlined it on the right. Now we're looking at a base framing condition of 16 gauge structural steel studs at 16 inches on center. So without resilient channels, we saw that wall a couple slides ago. That's STC 35. It's a low STC wall, again, driven by the stiffness of the framing condition. But below, as soon as we introduce those resilient channels between the framing and the gypsum panels on one side of the wall, you see a huge increase. So resilient channels can dramatically improve STC, especially when the base framing condition is very stiff, as evidenced here with the 16 gauge, 16 inch on center studs. So with the EQ20 studs, we saw about a 5-point increase with the resilient channels, but with the 16 gauge studs, it's a 13-point increase. That's significant. That's a lot. So we're going to take a little side quest right here. I have more influencing factors to discuss momentarily, but I do want to talk about resilient channels a little bit because you'll notice here, in the highlighted portion, I mentioned high performance with a little asterisk. This is to address that. So to address it, we have to talk a little bit about some history. USG invented the original resilient channel. It was called the RC1. This goes back to the 60s, the early 60s. I pulled some images from an old USG gypsum construction handbook. You can see what that resilient channel looked like. There's some illustrations here, a photo on the right. 1/2 inch depth, 1.5 inch flange width. You'll see that there were these long, here, I'll bring this up, these long slots that were cut out of the web of the channel. And these characteristics are key because they really promoted significant improvements in STC. They were very, very effective at decoupling the gypsum panel from the framing and resulting in high STC. They also improve fire performance, especially in horizontal assemblies. So the resilient channels, again, were invented to improve sound and fire performance. So over the years, since the advent of that original USG RC1 in the 60s, you saw a lot of UL or pre-UL. You saw a lot of fire-resistive horizontal assemblies incorporating resilient channels between the joists and the gypsum sealing membrane. And that is because those resilient channels help maintain the integrity of that fire-resistive gypsum membrane during a fire test or a fire event. When those joists might be moving, shifting, charring, the resilient channels keep the gypsum sealing intact, and that is the primary fire-resistive barrier. So over the years, UL fire resistance designs are having, for floor ceiling assemblies especially, you see these resilient channels come up a lot. And I'm highlighting, this is an excerpt from UL design number L570. It's a wood I-joist floor ceiling assembly. You can see the resilient channels there in the image, item number 4. And this is how item number 4 is described in that design. It just simply says resilient channels formed of 25 gauge galvanized steel. It's a very, very simple description. But that basic prescriptive description has allowed for a number of different resilient channel designs to come on the market over the years. You'll have slightly different dimensions, different profile shapes, steel thickness. As long as it meets the 25 gauge minimum shown in the UL design, then it's appropriate. But we're seeing different punches in the web. I noted the elongated slots in the original USGRC1. You might see smaller ovals or circular punches or no punches at all. Sometimes you have pre-punched screw holes, sometimes not. So it allowed for a lot of flexibility in resilient channel design. And so these different resilient channel designs meet the intent of the UL design, of the fire resistance design, but they do not all perform the same acoustically. And so I'm not going to talk about all of the other different resilient channel designs and the ones that don't perform well. I want to highlight the high performance options. So I mentioned high performance resilient channels. These are 3 options that are currently on the market, and you'll notice some similarities between them. These are the key characteristics to look for. You have a wide flange. So quote unquote generic resilient channels may only have a 1 1/4 inch wide flange, but the high performance alternatives have usually a 1 1/2 inch to 1 3/4 inch flange width. You're looking for those elongated slots in the web, and you can see that in each of the 3 images here. And you'll also notice they have pre-punched screw holes that are centered on those slots. That is because when installing the resilient channels, those slots should be centered on the framing member. That is really a key aspect of the performance and in maximizing the STC performance of these channels. Also with these channels, you might find that the steel gauge or the steel thickness will slightly exceed the 25 gauge minimum noted in the UL designs. But this is what to look out for. So for, if anybody on the call is an architect or a specifier, resilient channels, these high performance options, they are now specifiable. You have 3 options. And if you're a contractor, you now have multiple options. And it's good to keep this in mind because invariably published literature, the STC and IIC ratings that you see in published literature, you should assume that they're using one of these channels. They're using a high performance resilient channel. If you use a channel that doesn't look like this, that doesn't have these characteristics, you should be expecting that your performance, your IIC, STC values are going to be lower than what you see in published literature from manufacturers or different design guides. All right, back to influencing factors. Presence of insulation. I mentioned insulation damps cavity resonances, improves STC. Certainly does. Here's the difference. Same wall type, with and without insulation. Without insulation, you're 8 STC points lower. So it is good habit, good practice. If you have a sound rated wall, fibrous insulation is probably the cheapest and one of the most effective ways to maximize STC. Spray foam insulations, they may claim that they're good for acoustics, but they should generally be avoided. Some testing was done by the Gypsum Association with closed cell and open cell spray foams in a couple different wall types, and the results were not promising. So be very wary of spray foam insulations. Also, spray foam insulations are more often than not allowed in fire resistance rated designs. So really, you have to consult the published design if you are building a fire rated wall and you want to use alternate insulations. And lastly, there may be minimal benefit to using mineral wool over fiberglass. Let's look at that here, because I think there's a preconception in the industry that mineral wool insulation, which tends to be higher density than fiberglass, is going to give you a tremendous boost in STC. That is not necessarily the case. As evidenced here, this is some gypsum association testing. The Gypsum Association did some testing a few years ago, not only of the spray foam insulations, but of fiberglass and a mineral fiber insulation in a couple different wall types. I'm going to show you just a quick summary here. On top, with fiberglass, we got an STC 48 in this wall, and with the mineral wool, it was a 49. Very small differences. Actually, if you look at the raw data and overlay the transmission loss curves, very, very, very minimal differences between the two insulation types in this wall. So you can expect small differences, but it's not, switching from fiberglass to mineral wool is not going to be a lifesaver. It's not going to increase you 5 points. So just be aware. Also, if you're using mineral wool insulation in walls with resilient channels, it's important to hold the mineral wool away from the resilient channel, because if the mineral wool rests on the resilient channel, it can actually reduce performance. It can interfere with the resilient channel's ability to perform. Gypsum panel layers. This one's pretty obvious. I mentioned mass, weight in that big table at the beginning. Obviously, if you add layers of board to a wall, you're going to see an increase in performance. That's what we're seeing here. Going from what we call on top a 1 hour fire rated wall with a single layer of type X both sides to 2 layers on both sides, we see a 6 STC point improvement. There's this thing in sound transmission called mass law. So theoretically, doubling the weight or the mass of a partition should increase transmission loss by 6 dB, which should roughly equate to about a 6 STC point increase. We see that here. It's not always true, but it's a good rough rule of thumb. And they're diminishing returns. As you add more and more panel layers, the improvement in STC is going to be smaller and smaller. Lastly, I want to talk about stud depth, and part of this is insulation thickness. Generally speaking, as your cavity depth increases, you are going to see an increase in STC as long as your insulation is growing to fill the cavity. So here's an example of, we have an STC 47 wall on top that's 3 and 5/8 inch studs. Compared to the same wall type, we're just changing those studs to 2.5 inch, and we lose a few STC points. I don't show a 6 inch stud wall here, but if we're going from a 3 and 5/8 inch wall to a 6 inch stud wall, you're going to gain about 2 to 3 STC points, provided that the insulation grows to fill the cavity. So I see we're running out of time a little bit, and I want to save time for questions. So I'm going to touch briefly on influencing factors related to IIC. This is a very similar table that we looked at with STC, but I've highlighted 2 things. So what I want to say is, all of the things generally that improve STC will also tend to improve IIC. The 2 highlighted items here, carpet and pad and resilient floor mats, really points to it's the floor system itself that is probably the most significant influencer on IIC when we're talking about framed cavity construction. So I'm going to show you a couple examples of this. So here's 2 assemblies. These are UL Designs H505 or G556, steel C-joist assemblies, resilient channels, subfloor layer, structural concrete subfloor. And the one on top, STC 54 IIC 27, that is IIC on the bare, tested with the bare concrete panel subfloor. That's very low IIC. It's because the hardness, the surface hardness of that concrete subfloor panel. By comparison, as soon as you put carpet and pad on top of there, your IIC jumps up to 71. You've made a cushion, right? When the hammers on that little tapping machine drop, they're not generating a lot of energy because they're landing on a cushion. So carpet and pad is extremely influential on IIC. If you want to guarantee high IIC, use carpet and pad. But recognize that carpet and pad is not always in fashion, not always an option. So let's look at one more slightly different option where, again, the assembly on top is the same one that we looked at before, bare IIC on the subfloor panel of 27. Below, okay, you've taken away the carpet and pad, but you still need to meet your IIC 50 code minimum. What do? And you can see there's a little bit of a buildup on top of the subfloor, consisting of a sound mat, a resilient sound mat, a couple layers of a gypsum fiber board, and then ceramic tile. So ceramic tile is hard. When that tapping machine is tapping on those ceramic tiles, it's making noise, it's generating energy, but below those layers, you have that sound mat. And so that is helping reduce how much of that impact energy transmits into and through the assembly. So that's how you achieve your IIC code minimum of 50 or better. So really, I encourage you to look at the floor system. Look at your finished flooring, look at the buildup on top of your subfloor. That's really going to drive your IIC in these types of assemblies. So some strategies for success. Let's start with some do's and don'ts. And I'll move through these pretty quickly, but do seal all penetrations and intersections airtight with acoustical sealant. So if air can get through a construction, so can sound. So we want to seal up any intersection conditions, penetrations. You don't want to leave walls unsealed. Even small cracks and gaps in walls can reduce the STC value or the sound transmission performance of a wall. Here's an excerpt from the GA 600 manual. The same table that you see here is also in ASTM C919, which is the standard for acoustical sealant or use of sealant in acoustical applications. But it basically shows that if you leave your perimeter of your wall unsealed, you're going to have STC 31 in this case for the wall that was tested. But as soon as you add that sealant around the perimeter on both sides, you're up to STC 51, 52. So it just shows the importance of sealing your intersection conditions, sealing your penetrations, making everything airtight. Do offset penetrating fixtures on opposite sides of the wall by at least one stud bay. Don't place those penetrating fixtures back to back. What do I mean? I'm talking about electrical boxes. Same holds true for cabinets, mirrors, other things. But you see in this image, you want to avoid what's shown on the top there where you have outlet boxes back to back. You're just inviting sound to transmit directly through. A better option, you keep them in the same stud bay, but you offset them with some insulation, or even better, put them in, offset them by at least one stud bay. A little bit of a belt and suspenders approach could be to add putty pad backers. So these are putty pads that kind of seal up the housing of the box, all of those little cracks and gaps and punch outs, makes it airtight, adds a little bit of weight and mass to that penetrating element. These are quite effective. Do use resilient channels to improve STC and IIC, but don't short circuit your resilient channels. I want to show the difference here. In the image here, you see that the gypsum panel is screwed into the resilient channel, but the tip of the screw does not penetrate the framing member. If it does, it's what we call a short circuit, and that's a surefire way to reduce the STC of your otherwise high performance wall. Don't short circuit your resilient channels. This happens all the time. We see it regularly. Sometimes it's hard to avoid. It really takes careful installation. Do use resilient channels, again, to improve STC and IIC, but don't sandwich resilient channels between panel layers. That's what's shown here in this image in the upper left. It's maybe hard to see, but sometimes, and we see this a lot in wood-framed multifamily construction, but in all sorts of construction, where you need a wood structural panel for shear. And so when you have that, I often see resilient channels are attached to the wood structural panel, and then gypsum panels are attached to the resilient channel. So you've sandwiched the resilient channel between panels. And that largely eliminates the benefit of the resilient channels. So we try to avoid that condition at all possible. Keep in mind that there are some UL designs that actually require the resilient channel to be placed between panel layers, most often in horizontal assemblies. One example is UL L511. When you see that, when you see a resilient channel in a published design sandwiched between panel layers, it's not for acoustics, it's not helping for sound, it's really for fire resistance. Lastly here, do use resilient floor mats to improve IIC. but don't screw through the mat into the subfloor. If you screw your finished floor or if you staple the mat, you're just inviting, just like I showed the short circuits for resilient channels, this is kind of short circuiting your sound mat. You're gonna start to hurt the IIC benefit that you would otherwise get with your resilient flooring materials. Try to avoid that. And lastly, plan for sound. So this is a little bit of a recap from some of the discussion earlier. So please remember that there's variability in STC and IIC. I really encourage you to think about these values in terms of ranges and design with that variability in mind. Framing conditions, as I mentioned, the base framing conditions tend to drive STC ratings. So be aware of your need for structural studs. If you have load-bearing walls, or if you're going to have a very tall wall where you need heavier steel to reach those limiting heights, that's really going to affect your STC ratings. Carefully review your partition schedules. If you're a designer, really scrutinize and be thoughtful when you're putting together your partition schedules. If you're a contractor and you're inheriting a partition schedule with STC ratings, look closely at those ratings and make sure the STC ratings are applicable to what you're seeing on the drawings. And as I mentioned before, when we took that little side quest talking about resilient channels, not all resilient channels perform equally. A vast majority of published STC and IIC ratings assume the use of high performance resilient channels. So anticipate that. And these, if you're on the design side, these channels now are specifiable. There are 3 options. I know architects don't like to write a spec for one product or one manufacturer. Well, you have 3 options now. So I see these things as being specifiable now. And if you're a contractor, good to keep this in mind for pricing, and you do have a few different options available to you in the market. So that's it. Almost right up against the hour, but if there are any questions, I'd be happy to take them.
Yes, there are a couple of questions that came in. So what's the scale for STC? Is it 1 to 100? And is it the higher the STC, the better the room acoustic?
Okay. Yeah, I suppose I should have covered that. Higher STC is better. Okay. What STC isn't really on a scale, like 1 to 100. STC is essentially the decibel reduction of that partition at mid frequencies. So I didn't get into the calculation of STC, but you can think of STC like STC 50. If you have a wall that's STC 50, it's reducing sound through that wall by 50 decibels at middle frequencies. So we're kind of like right in the middle of the human speech frequency range. So it's decibel reduction. IIC is not really the same, but generally speaking, higher IIC is you're reducing how much impact sound transmits through, but it's not really correlatable to STC, and it's not really a decibel reduction. But STC can be thought of as decibel reduction of that partition.
Great. Do you have a test that shows the performance variation between RC Deluxe, the dog bone, and the generic RC channel?
So I didn't, we had that side quest where I called attention to the high performance resilient channels and then everything else. We've done some testing here at USG where we've compared RC Deluxe. The new Philips RC XL is a very high performer as well. We've also tested some of what are known as RC1. So I also warn you, everybody on this call, the original USG RC1 is the original. It is essentially the same as the Clark Dietrich RC Deluxe now. It is the high performance original resilient channel. But the term RC1 has become kind of genericized. So you'll see a lot of products out there that are called RC1, but they'll look very different from the original USG RC1. They'll look very different from the high performance channels that I showed on the earlier slide. USG has done some comparative testing. I know some acoustical consultants that have done some comparative testing. Generally speaking, if we're talking about the difference between those 3 high performance options and everything else, you could be talking about a difference of 3 to 7 STC points. So with the alternative, the non-high performance options being 3 to 7 STC points lower than the high performance alternatives.
All right, next question here. In the round robin testing with the single layer on each side, the STC ranged between 47 and 51. What type of top track was used, and did drywall fasteners go through the head of the wall track?
That's a really good question. So again, that particular wall system, it actually used a 25 EQ. It was a Clark Dietrich Pro Stud 25 stud and their Pro Track 25, if I remember correctly. And in UL U419, which is the non-load bearing, I referred to it repeatedly in this presentation, which would apply to this wall system that was tested in the round robin. In the UL design, the studs are friction fit into the tracks. So the studs are not screwed into the track at the top and bottom. However, in the testing for the round robin, we were instructed to fasten the steel studs to the top and bottom track. So those results that you saw, the STC 47 to 51, were with screws placed in the attaching the studs to the top and bottom track. A little bit of a departure from how we would test a fire rated UL design U419 wall.
Okay. Does the added cost of a sound breakboard sheet worth the money to you?
Okay, so a sound break panel that's from National Gypsum. There are other similar kind of quote unquote high STC panels. These are laminated gypsum panels. They use the constrained layer damping method that I spoke briefly about earlier. They are expensive. They have their applications. I think it's really on a case-by-case basis whether or not they are worth the added cost. I have seen situations where, you know, again, you have a stiff framing condition, you can't use resilient channels. Our approach at USG is to use standard products, you know, standard, or even upgrade from like a standard 5/8 type X to a heavier abuse resistant panel to get some mass benefit. Use resilient channels, adjust the framing conditions in a way to obtain higher STC, not from a product, but from a system. But sometimes that's not always possible, and there are certainly applications for those products. But it's hard to say a blanket yes or no, they're worth it or not. I think it depends on the conditions at hand.
Thank you. And then we're going to conclude with this question here. Where can I find documentation on tested wall ceiling assemblies and the corresponding STC rating?
That's a great question. So USG has guides, has STC guides for tested assemblies for, you know, our wallboard products, you know, and as well as our, you know, some of our products that go in floor ceiling assemblies. Maybe what I can do, Tao, I can attach kind of a resource slide at the end of the presentation. There are also, you know, so you can find other gypsum panel manufacturers and other building product manufacturers. They have their sound guides. There are some more kind of generic guides out there as well. The National Research Council of Canada, it's a government body. They have a fantastic lab and they do a ton of testing, and it's all free. And it's available to the public. The Gypsum Association publishes the GA 600 sound manual, fire resistance and sound manual, which has a lot of STC ratings for a number of different wall and floor ceiling and horizontal assemblies. So what I may do is I can put together a couple resource slides with some links.
Great. Thank you so much, Andrew. On behalf of AWCI, thank you for that wonderful, informative presentation. Thank you to all the attendees for joining us today. If we didn't get a chance to answer your question, please feel free to reach out and we'll be happy to pass that along. And then you can catch the recording along with the handouts in the next couple of days. Thanks so much, everyone. Have a great rest of your day.
Thank you.